It's nice. Normally I have to give the talk first before I get the applause. Thank you very much. Thanks for the invitation. It's a great pleasure to be here, and it's been a great pleasure to spend my day talking to all of you and switching subject every half hour. I'm going to switch a lot of subjects in the next 45 minutes or so, and then we'll see how you're doing and whether I continue or not. You're my guinea pigs for today. I'm going to try to do something that I haven't done before, and I made a few baby steps toward that end to try to do for the mantle what we have done 60 years ago for the plates, and that is try to make kinematic reconstructions of how the mantle is convecting. But before I do that, I'll give you a brief introduction of who I am and how I got here. I'm a field geologist. I studied geology because I wanted to see the planet, and it's working. I really like it. And this is field work here, for instance, that I did with my friend Mélodie Philippon, who's a professor at the University of the Antilles. So you can see why she's my friend. It's a very nice place. This is on the island of Richard Branson. He lives there, in the Virgin Islands. And we got to sample a section of volcanics there. So I really enjoy doing field work, and I do that field work to do paleomagnetism, structural geology, stratigraphy, and work out tectonic histories. And based on that, my group and I try to construct the modern architecture of orogenic belts. And from that architecture, make kinematic reconstructions of how those belts came to be. And that can be, for instance, in the Andes, crust that is simply squeezed, lithosphere that's squeezed together and making a big mountain belt. But let's say the kinematically very challenging parts are the accretionary origins, like here in Japan, for instance, in Kamchatka, where lots of infrastructure that was once spread out over 10,000 kilometers got scraped off and merged together. And those are the records that we have to make reconstructions, not only of the tectonic plates that we have today at the surface, but also the ones that have been lost to subduction. And those regional reconstructions we can then integrate into global reconstructions. This is something that we're working on. It's not finished yet. That is that reconstruct not just where the big plates were, but also how all the infrastructure that existed between those continents that we now have merged together, what that looked like. And from there, I can go two ways. One is up, and that is trying to make quantitative paleogeography models, and I've been discussing that with some of you here today, that is actually really difficult. And from that, you make tools for paleobiology, paleoclimate, and I'm not going to talk much about that today, but I'm going to do a little shout out in the next slide. And we can go down, particularly through the process of subduction, but also through records of mantle plumes, for instance. We can go down into the mantle and then basically do the same trick for the mantle. Work out mantle structure, mantle architecture, if you like, date it, do mantle tectonics, and from there on, try to say something about the dynamics. Now, that is the subject that I will be talking about today. A little shout out for 10 years ago, we made a model called paleolatitude.org. It's an online tool, and we made that for the paleoclimate community because you need to know at what latitude your climatic record formed in order to be able to interpret global climate evolution. And that original model had the major plates, like North America, South America, but we did not include the orogenic belts, which are highly mobile and much more difficult to reconstruct. And for climate records, that's fine, because if you want to know paleoclimate, you're not going to go to the Himalaya, but do some passive margin. However, this tool became used quite widely by paleobiologists and people who study fossils, and those come normally from the exposed mountain belts. So I spent a sabbatical 2 years ago. I spent months drawing polygons, because if you include the mountain belts, suddenly you have to go from a few dozen to a few thousand polygons. But that is now finished. And if you want to test that, it also has batch options, so you can throw in loads of data and get paleolatitudes. If you want to play with this, it's now available on paleolatitude.org/test. Play with it. If you find hiccups, things don't work, let me know. We're getting this published in the fall or so, but I want to get all the hiccups out. But today's talk is not going to be about that. It's going to be about the mantle. 100 years ago, Arthur Holmes introduced the concept of mantle convection. He said that if there's heat sources, he was big on radioactive decay, if there are heat sources in the mantle and we have a viscous medium, then it'll start to convect. And around the same time, Alfred Wegener came with his idea of continental drift, and he put 2 and 2 together and argued that perhaps these motions in the mantle could drive the processes that we see at the Earth's surface. And as a part of that convective behavior in the 1970s, Jason Morgan figured out that there might be mantle plumes that rise up through the mantle and that are part of systems like that. In the 1960s and 70s, we realized that the Earth's surface was broken into tectonic plates that move relative to each other, and that those plates, once they age, become denser than the mantle and sink and drag plates along the mantle. And now we have 2 drivers of the change that we see, 2 potential drivers of the change that we see at the surface. Plates that sink and a mantle that convects. And I don't know what you guys teach here, but what I was taught, for instance by Trond Torsvik, with whom I worked and who has been influential, is that these 2 things form a coupled coherent system. That plates and mantle together, that the plates are part of a large convecting mantle, and that somehow drives everything that we see at the surface. But the thing is, that is an assumption. We actually do not know from observations how the mantle is convecting. We know from models how it could convect, right? Numerical models give you basically an indication of how a viscous medium with a certain viscosity could behave. But we have very little observations how the mantle is actually moving. We have very little reconstructions. And if you compare this to boats let's suppose that I would have come from Europe yesterday by boat. My boat would have had an engine. It wouldn't have worked in a day, but my boat would have had an engine driving my boat westward. But at the same time, I'm going over a mantle conveyor belt in the Atlantic Ocean that would offset my boat northward. And those 2 things, one is convecting and the other one has its own engine, and those 2 things do not have to work in tandem. They could work separately. So, if we want to know what the contributions are, and it's kind of urgent, because here I'm standing on a plate that is moving 2 centimeters per year to the west over the mantle, and as far as I know, nobody understands why. At least I don't. And South America is doing the same thing. So right now, 60 years after we figured out plate tectonics, we still cannot explain why the plates are moving in the directions they do at the rate that they do. So can we reconstruct how the mantle is moving? And for me, this game started at the end of my PhD. I was working in Greece. Some of you are too here. And Greece basically consists of a series of rock slices that were off-scraped from a downgoing plate. They consist mostly of sediment, a few kilometers thick, here and there some basement underneath, and they are stacked on top of each other. And all of those slices you can see here as different colored bands in Western Greece. And from that orogenic architecture, somebody asked me, where's the lower crust? Why is it if I go to these accretionary origins that I always find upper crust? It may have gone down, become blue schist, but it was upper crust, on upper crust, on upper crust, on upper crust. Where's the lower crust? Because a lot of this stuff came from continent. And I thought that must have then been subducted. So we made a reconstruction, a very simple one, in which we simply put all those naps that are now on top of each other next to each other, and figured out, also in combination with plate reconstructions, how much lithosphere then should have been subducted under Greece in order to, in order to get rid of all that lower crust and mantle lithosphere. And then we compared that to tomography, and we found the same volume, roughly the same volume in one slab in the tomography. Now the controversy at the time was that 900 kilometers of this slab must be continental lithosphere. By now we've gotten used to this a bit more. But the more important point that I didn't realize at the time is that this was a way, for the first time, to date tomography. Right? This is a few years after we had the first global tomographic models in which we showed, we could see large anomalies that were probably plates that subducted. But this became a way to use orogenic geological records to date when this piece of slab entered the mantle, and therefore how fast it sank. Now since then, I've spent a lot of time on making reconstructions that are a bit more complex than that simple cartoon that I showed in the previous model. And this is something that, this is 6 seconds, but it took 10 years. I was hired by Trond Torsvik to make a reconstruction of the Mediterranean region in 2009, and we published it in 2020. So sorry. It was a bit complex, but models like this showed the variation, the along strike variation. This was what was really cool about this is that in the time that I started this postdoc in 2009, a software called G-Plates that you are probably familiar with just came out. It was in the beta version, and I could play with this to see if we could use it to reconstruct deformed regions rather than just fixed plates. And the answer was yes, but it took a while. So we had this one. This is a model that a reconstruction of my PhD student Susanne van der Lagemaat, an Eldert Advocaat, of the Southeast Asia, which is another geological mess. Southeast Asia has bits and pieces here called Argoland that broke off Western Australia that went north, and then we reconstructed the junction region between the Tethys and the Panthalassa region, and worked out plates that must have existed and that were lost through subduction. And then there's one that is about to be submitted. This also took 6 years, this little clip, of how we can make those reconstructions of origins here in the case of Iran and Afghanistan, whereby we show that there is enormous extrusion from Western Tibet to fill a big backward basin that was Iran. Now this is a lot of geological information in a few seconds, but it just goes to show that with these reconstructions we have a pretty strong basis to now really interpret the geological history of subducted lithosphere and link that to subducted slabs in the mantle. And we started doing that with a friend of mine, Douwe van Hinsbergen. He's a bit of a funny guy. He did his PhD. He got his PhD with honors in 2017, but he's never been a PhD student. He was a master student at the time that I did my master with Wim Spakman, and he was doing trying to interpret the seismic tomography and the configuration of slabs below the Caribbean in his master in 1999, 2000. And he decided that he couldn't make up what was Caribbean and what was not unless he also incorporated the Americas. And that became a master thesis, but then he decided that you cannot see what is America unless you see what is Russia and etc. So this became global. And for 17 years, when we saw each other, we did a slab. We figured out a new slab, figured out what the geological history was. And this way, slowly, we made a systematic interpretation of the slabs in the mantle and their geological history, under two simple assumptions. One is that deeper slabs tend to be older than shallower slabs. And the second one was that slabs that are now north and south from each other subducted north and south from each other. In other words, after slabs broke off, they don't do this. Under those assumptions, we started to correlate shallow slabs to younger origins and go deeper and deeper. And what came out of that, first attempt in 2010, was a sinking rate of slabs through the mantle, which was surprisingly constant and surprisingly slow, about 1.2 centimeter per year, which is a lot slower actually than plate motion rate, which means that slabs have to thicken. They buckle in the transition zone, they have to thicken. One thing that I realized much later is that basically means that slab pool is concentrated only in a few hundred kilometers of the upper mantle and the rest of the world is resisting it. I have to do something with it, but I don't know yet what yet. But so that's the first thing. The other thing is that the slab configurations that we see in the mantle still seem to match reasonably the subduction configurations at which they subducted. And what that means is that on eyeball statistics, and now we have to do this quantitatively and much better, and I hope to be able to start doing that soon. But what it means is that slabs seem to sink more or less vertically, as slowly through the mantle. Now, we kept doing this, and this is the next 7 years of our life. This is what we call the Atlas of the Underworld. Douwe has also called Douwe, has an interesting way of finding nice titles for his papers. So the Atlas of the Underworld with all of these slabs. Douwe and I once spent a night in jail in Greece. We were arrested for illegal sampling. And the first question that they asked us, is Douwe a common name in the Netherlands? No, it isn't. But Anyway, we were released, but he got a job at Shell because of that story. Where were you last week? Well, during his job interview. Anyway, these are now 100 slabs, so the data set became bigger. And with those slabs, we could start to compute in situ sinking rates of slabs in the mantle. So what that shows is that slabs decelerate after they go through the upper mantle to something like only half a centimeter to maybe a centimeter a year. Then they may accelerate a little bit in the lowermost mantle when they reach the coronal boundary. This is mantle kinematics in 1D, just sinking. But this is the kind of stuff that is interesting if you try to figure out mantle dynamics. So this is something that we can use to calibrate models against. And I had a PhD student who graduated last year, Erik van der Wiel, great guy, who made models in which he tuned the viscosity such in the global seduction model that the sinking behavior matched what we reconstructed. Now this is a billion year of seduction. What we reconstructed is only the last 250 million years. A billion years ago, it may have been different, may have been faster, whatever. But just to show you, now we can start to use those models to get an idea about how lateral motion in the mantle could be, how fast that could be. So these are a whole bunch of tracers where he worked out how long it took for that tracer with a slab to go down through the mantle. That is, you see a red line here if you have very good eyes. That red line matches the averages that we reconstruct. So this is a reasonably successful tuning. And the outcome of that is that in this case, something like 90% of the slabs or so, 90% of the parts in the mantle have horizontal motion rates of only a few millimeters per year. Right? So if slabs sink at 1 centimeter per year through a mantle, it means that the surrounding mantle is moving slower. Otherwise, it's not sinking. So the rate of mantle convection that you would guess, predict, based on simply tuning the slabs is actually super slow. A few millimeters per year is a few hundred kilometers per billion year, right? Or a few thousand kilometers per billion. So the next challenge then becomes, can we reconstruct lateral mantle flow? And we might try to do that in that same analogy that I made earlier to how ships move over a sea that has currents. Can we reconstruct those currents? So the course of the ship is based on the direction and the speed caused by the engine and the ocean currents. If we now know how those boats move relative to each other, can we then reconstruct from some observation that we can link to those boats how fast those currents are? Now, what we then need to do is find elements in the mantle that we can link to the geological record. So let's say buoys, let's say that those ships deploy buoys, and we know where they do that, and we know how the ships move relative to each other, then we can figure out how those buoys may have moved relative to each other through that ocean underneath. Now, our buoys that we have is, for instance, subducting slabs, rising mantle plumes, and something else that I'll come back to that we now start to call ghosts. And then we can try to do something like this, try to see how much horizontal motions occur between those buoys, those, let's say, call a slab a buoy. The slab breaks off, leaves an origin behind, the slab goes down, the origin moves with a plate. But if we can reconstruct where the slab originally was, and we can see where it is now, we can get a motion history. Now, what we need to do that is some starting point. If we have no idea how those ships were moving over the sea, we need some basic model to suggest how the plates moved over the mantle. And normally we do that with what we call a mantle reference frame. There's an issue with a mantle reference frame. But things that you might be familiar with, what you're probably most familiar with is a hotspot reference frame. Right? If you want to, for decades we've said if we want to know how plates move over the mantle, you can go to Hawaii, you can see that there was a magma source, volcanoes pop out, you can date the volcanoes, so you can determine how a plate moves over the mantle. You have to assume, though, that that mantle source was stationary in the mantle. And we know from hotspots that they move a little bit relative to each other. The other way that we did is if the slabs are indeed sinking vertically, and we know their sinking rate, we can link subduction records and plate reconstructions to slabs that we see in the mantle. There are ideas to use some funny structures that we don't understand in the deep mantle. Some of you who work on the mantle will be familiar with them. They're called large shear wave velocity provinces, the most terrible name that we've come up with so far, the LLSVP, because that's what they are. They have edges, and it seems that plumes come from those edges, and that these things are stable. We don't know what they are, we don't know how they formed, and we don't know how long they existed. But at least we can get some idea. And this is an interesting one. A couple of years ago, Dietmar Müller and his group in Sydney came up with an idea to make reference frames based on tectonic rules, based on a bunch of assumptions or principles. For instance, if your mantle is not moving, and you have continents that move through that mantle, those continents have keels, and they will resist motion. Others are that you have slabs, and plates with slabs don't like moving horizontally through the mantle. That'll be resisted, so you can minimize those motions. Now, the big problem of a mantle reference frame, a reference frame basically means that you want to figure out one thing, you keep one thing fixed so that you can see how other stuff moves relative to that one point, right? Now, we've decided 100 years ago that the mantle is moving, that the mantle is heterogeneously moving, which means that we don't have a mantle reference frame, that we have an average mantle reference frame, but it means nothing, right? If we take Craig fixed and I move to him, that works. If I make an audience reference frame and you guys all start walking through the room, then we can take your average motion and my motion relative to that average point, but it means nothing. It does not predict any motion between me and you. So if we want to figure out how the mantle moves, we should not put, what we know is how the plates move relative to each other. So if we want to figure out how the mantle moves, we should not put the plates in a mantle reference frame, we should put mantle in a plate reference frame. And then we make one simple assumption. For instance, a probably wrong one. The assumption is the mantle is stagnant. It doesn't move, it's viscous, but it's stagnant. Then we can predict absolute plate motion. For instance, we're going to use the minimum continent motion reference frame. Because continents have a keel and they resist motion through that stagnant pond. And then we can predict independent constraints. We can use that model to predict hotspot motion, or to predict how hotspot tracks should have formed. And mismatches now inform us about motions in the mantle. So I had a rather bright master student, Steffi Wagenaar, who made that minimum continent motion reference frame. We took a plate model, global plate model of the Müller group, of Andrew Meredith, and we took 10 million year intervals and chose an Euler pole of that entire plate model in such a way that in each 10 million year interval we minimize the motion of continents. Under the rule, if the mantle is stagnant, the motions of the continental keels are resistant proportionally to continental area. Okay, you can make that one. The next thing is that we need to figure out uncertainty. It's hard to make uncertainty, but what we've done is the plate models have uncertainty, right? If we say this is the plate configuration 10 million years ago, it could have been 11 or 9. So what we have done is all those uncertainties that we have in geology, which are all sorts of, a whole basket of apples and oranges of uncertainties, we take a plus or minus 5 million year uncertainty. And we compute this model 1,000 times, and every time we take two configurations within 5 million years of our 2 points. And that way, we worked out, so focus on this one, we worked out for the continent frame what the uncertainty was, and the uncertainty until about 350 million years ago is smaller than the step. Right? So we can resolve that motion within error. Before 350 million years ago, it becomes hopeless, which is not strange. We lose plate circuits, right? So continents start moving all over the place. We have paleolatitudes that we can use for magnetism where we don't have longitudes. So, you know, plate models before 350 are kind of fantasy. is nice, but it's fantasy. And I won't start about supercontinents. I'll do that I'll fume about that when we have drinks. But so before 350, it's hopeless. That means also for the published frames, I don't know if any of you use them, but for the published reference frames, we now have them in 5 million year steps back to 2 billion years or so. But basically, the steps are always much smaller than the uncertainty. It's unresolved. So you can use those models if you want to have plate-like behavior in a numerical model or so, but don't start comparing to proxies because it's noise. But after 350, we're quite happy. So now we can use this to predict the motions of hotspots. We've used our reference frame to predict, if we take Hawaii fixed today, the Hawaiian plume, we can use our reference frame to predict where in 10 million year time steps that hotspot track should go if our assumption of the continent frame is correct. And then we get this black line with the uncertainties that we computed. Louisville in the South Pacific is that one. That is a remarkably close match. Essentially, what we say is that if the mantle is stagnant and we work with plates in the minimum plate reference continent frame, that the hotspots are actually also not moving, what you would predict, in the Pacific. Now, I already said in the beginning that hotspots are known to move relative to each other. You can see that in the plate circuit. You can simply see that they have to move a little bit. And indeed, the hotspots in the Indian Ocean, Kerguelen, the Kerguelen hotspot must move eastward at a rate of millimeters per year. And the Reunion hotspot is more or less stationary. The St. Helena hotspot has to move southwestward, and the Tristan hotspot southeastward. The funny thing is that so far we've always assumed that the hotspot in the Indo-Atlantic realm are stationary and that the ones in the Pacific are moving. This predicts the opposite. Now this looks like pretty much random directions, but it became really funny when I brought those LLSVPs back in. These LLSVPs, I just told you, are those things that we don't understand in the deep mantle, but what it seems is that mantle plumes seem to rise from the edges of those plumes up. Sorry, from the edges of those LLSVPs up. And now if you look at the predicted hotspot motions, Helena, Tristan, Kerguelen, they move parallel to the edge of the LSVP, which suggests, if this is right, which suggests that the foot of the plume, the root of the plume, is slowly moving along the core mantle boundary, which could be an indication of flow in the deepest mantle. There must be flow in the deepest mantle. Slabs still sink to the base of the mantle. That means that everything that was slab that did so before has to move out of the way. So there must be some form of motion. So assuming that the mantle is a fixed body of rock, predicts independent observations surprisingly well. Hotspots on 100 million year timescale. Slabs seem to sink roughly post-Vogel, but I told you it's eyeball statistics. We can do better. So are there other boys? And this is something that I find the most exciting development in solid earth science, and that many of my colleagues think were nuts. And it starts with Yamirka Rojas Agramonte, a good friend of mine, Cuban geochronologist who is now a professor at the University of Heidelberg. And she dates zircon, something that many of you are very familiar with. And she found zircons in places where they're not so well expected. Zircon is a very common mineral, particularly in felsic rock, and almost everything we know about the history of the Earth's continents we know from zircon. They're super resilient. You can subduct them into the upper mantle and they don't break down until you get deeper than 300 kilometers. You can keep them stable in mantle conditions if you encapsulate them in olivine. They can be accurately dated with uranium-lead dating. They're very common in continents, but they're very rare in mafic rocks. So we do typically not spend a lot of time looking for zircon in intraplate volcanoes or in oceanic crust. There is some, but it's so little that you can better date it with argon or so, or cooling agents. But Yamirka was a professor at the university in Ecuador, got the opportunity to go to Galapagos and thought, let's have a look what we find. Now, zircons in those mafic rocks are very rare, and if you want to get a big population, there's no point collecting rock. She did, there are a few in those rocks. But the better thing to do is to go to beaches. Because when you erode volcanoes, the zircons are released as sand grains, and they're heavy minerals. So if you go to places with wave action, that works like a natural gold pan, and your heavy mineral streaks your heavy minerals concentrate on beaches and your light stuff disappears. So here on the Canary Islands, this is J.D. Sauerbier, a South African PhD student that we have, who is now doing this also for biology purposes. But here on the beach, you see these dark streaks, and those are the heavy mineral streaks, a lot of magnetite and stuff like that. And there's quite a lot of zircon in there. This is Yamirka on an expedition to the Revillagigedo archipelago. I've been practicing that for a long time to pronounce. Which is the island of Socorro, west of Mexico. That was a fun trip. Melo again. So we found zircons. And also on Galapagos and on Easter, she found a lot of zircon. Now, the Galapagos is a hotspot, volcanic center, and so is Easter. And she collected the zircons from the beaches, from rivers, regolith, and in the case of Galapagos, also from a bunch of basalts. And these are Plio-Pleistocene volcanoes built on Upper Miocene or Pliocene oceanic crust. She dated the zircons, and she did geochemistry on them. And the results showed this. The first surprise, this is geochemical plot. These are the delta O18 values. These are hafnium values. And the first thing is that there are ages. The younger zircons all have compositions that are consistent with plume magmas, which is not surprising. The older zircons have very varied compositions and is basically a cluster that you would expect in a continental sandstone, which is odd, a few thousand kilometers from the nearest continent. The bigger surprise came when she added the ages. The plume-related zircons here on Galapagos date back to 170 million years. And the ones on Easter date back to 165 million years. They start with a cluster at 165 and 170, then have here and there zircon, and then there's the cluster of the very young volcano. This is the age of the ocean crust of Easter. This is a log plot. This is the age of the crust, and the crust of Easter is the age of the crust of Galapagos. And the zircons of the plume go back 150, 160 million years farther back in time than the age of the volcano or the underlying crust. The very varied zircons have ages from anywhere in the Archean all the way until the Permo-Triassic. So, where is this stuff coming from, and how does it end up on these remote volcanic islands? Is this contamination? Well, it's actually quite unlikely. When Yamirka found this first on Galapagos, she sent it to Nature, of course, and it was rejected, of course. Because every new finding goes through stages of ignoring, denying, challenging, and accepting. Except that when you're in the ignoring part, you're surrounded by crazies who find that their crazy thoughts are also ignored. So it's always a bit difficult to see whether you're one of the crazies or whether you have something new. But it's quite unlikely that... So the reason it was rejected by Nature is that the reviewer said, this is bird shit. Literally, that was literally the reason for rejection. You're looking at zircons that were eaten by birds on the continent, and then they were brought there and shat out on the island. We've actually done studies on how far a bird can fly without taking a crap, and they don't make it to the islands. But the bigger question, the thing that convinced me that we're dealing with something very interesting here, is contamination from where? If this would be contamination by wind or ice in the ice ages, with icebergs that go to the East Island or so, or ships why do we not find younger continental zircons? If you now would like to get a cluster of zircon that comes flying in from South America, there's an arc in the Andes. It's been active since the Cretaceous, or God knows how long it's active today. Why not finding that stuff then there? And the more important one, where are you going to get a record of 170 million year worth of plume zircon on Earth? A planet with plate tectonics doesn't have that. A planet with plate tectonics has plume material coming out, lava coming out, then it moves on. That's why we have hotspot tracks. The only location that I know where you could get in one place a set of zircons that span this age and have plume signatures is Olympus Mons on Mars. So unless this was planted by the Martians, I wouldn't know where else it could come from than from the underlying mantle. These might be xenocrysts that come from the mantle. Well, we can test this one step further using my plate reconstructions. These are the reconstructions of the South Pacific that Susanna van der Lagemat made. If we take at the modern location of the hotspot island in our reconstructions, where we have this cluster of 165 MA zircon ages, if we just draw a large igneous province, some circle, and we plug it in the reconstructions to see where it's subducted, because all hotspot material from Easter older than 40 million years are subducted by now, then it turns out that it should have subducted about 115 million years ago or so below the Antarctic Peninsula. And this coincides on the Antarctic Peninsula in the literature there with what is known as the Palmerland event, an unexplained phase of rapid shortening and change in the geochemistry that has been linked previously by a collision of a microcontinent, but the microcontinent is gone. So I was quite pleased with that. So far, so good. The implications of this for mantle dynamics are quite far-reaching. This is a very nice model that was made by Boris Kaus, a numerical modeler in Mainz. And what it shows, they made this in a 2022 paper, and what it shows is a model in which a plume comes up and creates some melts, and it tracks where those melts and the zircons that would form in them, where they would go. Now, the plate at the top is moving to the right. The mantle here has some small-scale convection around the plume, because material is moving, but it doesn't have a lateral motion. There is no mantle wind that would move with the plate. The plate is more or less decoupled from the underlying mantle. And what you see is that the old plume material accumulates in the vicinity of that plume. Now, one thing that I thought was very elegant is that you see that the plume is being dragged here with the plate, the volcano, and the underlying magma conduit are moving together until the elastic band snaps and we start to make a new volcano, and it snaps and we start to make a new one. This is why we have, I think, seamounts instead of a big dike. I never understood that. Why if we have a mantle source here, why do we simply have a big dike? But this is a way of doing that. And every time that it snaps, it could sample older material of that same plume and bring it to the surface. But what the implication of this is that the upper mantle underneath these plumes with these old zircons does not have a horizontal component of motion. If the mantle here would have been moving, the upper mantle would have been moving at the same rate as the plate, let's say, all the old zircons would be washed away. Basically what this means is that that plume can locally convect a little bit in that mantle, but the rest of that upper mantle underneath the plate must be decoupled from the plate and stay in place. Otherwise, it would be gone. The older zircons, the sandstones, I think my next slide will say something about that. Yeah. The older samples, the sandstones are, I think, sandstones that were subducted in mantle wedges, probably around Gondwana. One thing that Jamirka showed 10 years ago is that here zircons from the Orinoco River that are subducted below Barbados come up as xenocrysts in the modern volcano of Grenada, which means that those zircons go down into the mantle, enter the mantle wedge, enter the arc melts and can go to the surface. They survive that. That means that if that arc shuts off, that subduction shuts off, there is a bunch of zircons that come from an old subduction history and they stay in place, they stay there. So the implications are that the mantle is not moving very much and that it doesn't mix. At least not on timescales of 170 million years. Now, these former wedges, former plume heads, we start to call ghosts. We found a few, serendipitously. There's one that we actually searched for, wasn't there, in Socorro. But these are potentially new buoys deployed from our plate circuit that we can start to use to reconstruct how the upper mantle is moving. The consequences that I just explained are far from accepted. But I don't really see an alternative right now, but maybe there is. But this is one way forward. So, assuming that the mantle is fixed predicts independent observations surprisingly well. Not only the hotspots and the slabs, but even the ghosts. Now, is there any evidence that the mantle is vigorously convecting and mixing? What I've always thought, and what I've been taught, and what we show in our models. Is there any observational evidence that it's actually doing that? So far, I can't find it. Now, there is one more way in which we could do this, and could get an indication. That is through a process called true polar wonder, but I want to know from the chairman whether my red light is flashing.
And there's probably some questions, but you can go ahead.
Yeah, but that'll take another 10 minutes. So are you ready for that, or shall I leave it here? Silence is agreeing that I continue. So if you want to make noise, this is your time. No, then I'll try to be quick. One last way in which we can try to figure out how that mantle is moving is by a process called true polar wonder. And that starts with paleomagnetic data. So a shout out to your paleomagnetist here. He's important. And he invited me, but he didn't pay me to say that. Paleomagnetic data. With paleomagnetic data, we can make so-called apparent polar wonder paths. What that means is if we take India today and we would measure the paleomagnetism in the Deccan Traps, then we get a paleomagnetic direction, and with that direction comes a pole. We can predict where the magnetic pole was when those rocks formed. And what you will find is that that pole does not coincide with the modern North Pole. That is not because, so it seems that the pole wandered. The pole didn't wander, India did, right? So because India moved north, that pole is now located somewhere 45 degrees south on the other side of the planet. Now these apparent polar wonder paths are the result of two sources of motion of crust that we measured relative to the pole. One is obvious, plate tectonics. The other one is a little less obvious, and it's called true polar wonder. We are sitting on a spinning object, a spinning sphere, more or less. And the equator of that spinning sphere is determined by the maximum moment of inertia. Basically, the maximum average density on Earth aligns with the equator. So if you start to perturb the density structure of Earth by mantle convection, by subduction, by plumes, then the Earth, the spinning solid Earth, will readjust itself relative to the equator. For instance, if you have a slab that starts to subduct at high latitude, you replace a buoyant mantle with something dense, and that density will drag the planet towards the equator. There are more effects. It's not that straightforward to figure out exactly what the causes and consequences are. Modeling can help a lot with this. But true polar wonder, the rate of true polar wonder, is a measure for the rate at which density changes in the Earth's interior occur. So it's a measure for the rate at which mantle convective processes occur. The state of the art until 10 years ago or so was that true polar wonder is slow. The true polar wonder occurs at the same rate as plate tectonics. That's actually quite fast. Eh? That is why you should always, if you do paleoclimate, you should always use a paleomagnetic reference frame and not a mantle reference frame, because mantle reference frames, apart from the fact that there is no such thing, are blind for true polar wonder. They only show what continents do relative to mantle, but not what to do together. So that is why you should use paleomagnetism. What we saw in those estimates, and I'll show you a bit how we made them, is that there was, for instance, this big kink of 20 degrees back and forth in the Triassic and Jurassic. you probably don't remember, but I showed you that little image of my paleolatitude.org shout out. There I had 2 points. I can do that later. There were 2 points. There was Austin and Utrecht. And you saw in the Triassic and Jurassic that they diverged in latitude. But we were the same plate back then. Since then, we've diverged. But we were the same plate. So what you're looking at there is not plate motion, but the fact that you guys went south and we stayed at the same point. That was true polar wonder. In the recent years, however, there are papers that are filling Nature and the Nature satellite journals with arguments that there is also very rapid true polar wonder. We give them very prosaic names like the monster polar shift in the Jurassic, not coincidentally in the time period where we have the smallest data set. But we see there rates of motion that are argued for that are up to 30 centimeters per year, back and forth in 5 to 10 million years. If that is right, then we have a smoking gun for super rapid changes of convective motions in the mantle. The question is it right? This is the apparent polar wonder path that Trond Torsvik made. I'm going to criticize this. I'm a co-author. I was very happy with it when it came out. It's my best cited paper, but it's wrong. Trond doesn't agree maybe with me, but we did. I'll explain this in a bit. So here you see the red dots, and those are the average positions of the pole that we. This is made for. This is the pole from an Africa point of view, and what you see around that, those dots are the input data that go into the pole, into that average, and you see a huge scatter. So if I take 1 or 2 of these points around that scatter, and I say, look, a kink. We have to be careful. And so what we have to realize now is, can we quantify true polar wonder? How do we do this? Until 2012 or so, when we had the last big apparent polar wonder path revival, we made paleomagnetic averages that are frankly embarrassing. We've done this for decades, and paleomagnetists have not made friends with many people this way. Because what we do is we compute so-called paleomagnetic poles. Craig and I both did this. We're both guilty. We went to places, for instance, in Tibet. Craig collected 23 lavas or so, and I collected 60. And somebody else collected 7. And he took an average, and I took an average, and somebody else took an average. Craig had an argon age, or uranium lead age, that was 69.1 plus or minus 0.4. I had a stratigraphic time span, and the next one of 5 million years, and the next one guessed, based on the geological map, what it might have been. We now have 3 data points, according to paleomagnetism. The amount of samples, the reason that we take many samples is that, okay, I'll come back to that. So we have now 3 data sets. We ignore the uncertainties of position of the poles, we ignore the number of data that we used for the poles, and we ignore the uncertainty in age. And then we start to average those averages of averages. And we get a path, and we compute an uncertainty of that path that is entirely dependent on how we averaged those data points, and the way we did that is completely arbitrary. There are 2 poles from the Deccan traps, one with 130 lavas, one with 3, they count as NS2. We knew that this was not entirely right, but okay. And then came Dave Rowley in 2019. Dave unfortunately passed away last year. Dave and I had heated discussions about the paleogeography of India. I had my pet model in 2012. He disagreed. I wrote a comment, he came back with a reply. That reply cost me 5 years of work. Because what he said, what he showed, is that 50% of the poles that were used to make the apparent polar wonder path of Torsvik are statistically displaced relative to that apparent polar wonder path in the way we compute things. To translate, that means that if you find a pole that is different from the average, you have a 50-50 chance that that might mean something. And that is not a great basis to compute true polar wonder. So what Dave argued is paleomagnetism is essentially useless for tectonic purposes because it has a resolution of maybe 2,000 kilometers. And that was a problem. So fast true polar wonder is not resolved. The question is whether true polar wonder is at all resolved. I, at that time, hired Bram Vaas to make Mantle reference frames. And I said, Bram, we have a problem. We need to look into this first. We need to write the first chapter of your thesis to solve this problem. That essentially, because we have now a cart of paleomagnetism that carries paleogeography and plate tectonics, but is riding on square wheels of statistical procedures. And that did not become that became his whole thesis, and he never got to do Mantle reference frames. The first problem that we have, the reason that we're taking so many samples is that the Earth's magnetic field is wandering around like a drunk on timescales of thousands of years. This is the archaeomagnetic data set from North America, and it shows how the paleomagnetic pole, from a perspective of North America, has been wandering around in the last few thousand years. And you can see that it's curving around in a circle of something like 25 degrees or so around the North Pole. So if we take one measurement, we're somewhere within 25 degrees of that pole. But if we take a whole bunch of them, the more we take, the better we average and the better we approximate the true North Pole, provided that we do that over a sufficiently long time span of a few tens of thousands of years or so. So what we should combine are the readings of the pole, of the magnetic field, not the averages of those readings. So we've done it again. We had the next problem, and that is that much of the paleomagnetic data, especially legacy data, the original data are lost. We've published the statistical values of averages of them, but the original data are gone, and even to this day we're quite lousy as a community in making our data publicly available. So we had to do a few tricks, and I'll spare you those details, but basically what we did is we recalculated the apparent polar wonder path, but now not based on the averages, not based on the study averages, but on the data that were with an approximation of the data that was underneath that. And that means that we went from 350 to 13,500 data points. And we could now bootstrap uncertainties in age and uncertainties in position and weigh poles against different data sets and other artifacts such as inclination shallowing. We could bootstrap and propagate all of those uncertainties into the final answer. To our relief, we reproduced the apparent polar wonder path of Trond reasonably well. If that would have been totally different, paleoclimate would have had an issue. So that worked reasonably well. There are a few differences. The main differences are that the uncertainty has decreased significantly because we use the actual number of data, and the uncertainty is simply a function of how many data points you use. It overcomes Rowley's problem. We've figured out a way in which how we can compare small data sets to very large data sets in such a way that 95% of the data sets that we used for this are actually not displaced to this, such that if we find a difference, we have a 95% certainty that it means something geologically. And there are subtle differences in age because we can take the actual age of the pole into account, right? If you have 1,000 data points, but 400 come from one end of your spectrum, then your average age is not halfway. Okay, can we resolve true polar wonder by this? We can. We published a paper with Bram and I published a paper about this true polar wonder thing earlier this year. We can. What you see here are the paths that are predicted by the Mantle reference frames. They're much shorter than the paleomagnetic frame. Oh, this one is the same length. And the paleomagnetic frame, and you can see that they're different. And that they're significantly different. Now, I show you here the result with that earlier frame that I showed, that continent frame. And what that continent frame suggests is that there is significant true polar wonder in the last 150 million years. It's a few degrees, which is relevant but not spectacular. And then before that time, we get that bump that I talked to you about earlier, why Austin and Utrecht did something different. And then here we get something that I'm sure we will have a lot of discussion on with the rest of the community. But basically what it argues is that in Pangea time there was enormous true polar wonder, and that the motion of Pangea from southern hemisphere to the equator was almost entirely true polar wonder related. And frankly, I think that that is likely. But it has implication for LLSVPs. I'll spare you those details. But the main point is that with what we can now say about true polar wonder, the positional uncertainty is resolved. We do see significant slow true polar wonder on plate tectonic rates, centimeter per year rates. But the problem is that the temporal resolution of apparent polar wonder path, the present apparent polar wonder paths, is way too low to determine fast true polar wonder. And the reason is that we still have these long averages of pole ages, of data set ages. And it's rather, the solution is rather simple. This here is the Westerholt climate curve since, 70 million years, 65? Published in Science a couple of years ago. And what you see here is the highly detailed climate records with the PETM, with the Middle Eocene climate optimum and the Eocene-Oligocene transition. These are the things that the paleoclimate community has been discussing for the last 20 years. If we would have made this curve the way we make apparent polar wonder paths, we wouldn't have known of its existence. The way this was made is by using integrated stratigraphy. And so we have drill cores or we have sedimentary sections. We do magnetostratigraphy, biostratigraphy, cyclostratigraphy, tephra stratigraphy, anything that we can throw at it to get the best possible age model of long records. And then every individual sample that we take is assigned a very precise age, interpolated between known datums, and then a value, a delta OET value. We can also do this with magnetic values. We can figure out what the paleomagnetic direction is that that sample carries. And now we can stack, but with very high age resolution, individual directions, determine the uncertainty on that direction, and even propagate the sample uncertainty into the final average, and stack this from different continents and different times, and build very long records of high-resolution paleomagnetism. With this, we could compute apparent polar wonder paths at 100,000 year timescale resolution, and evaluate whether there's true polar wonder oscillations. This is a terrible job to do. Well, if you like stratigraphy and drilling, it's not, but I'm trying to get him so far to do this, because I don't want to. But I think, well, it's actually quite exciting to do this. There are all sorts of challenges to overcome, but we can do this. The question is it worth the money? We will never know, but just as a very, very last slide, every time that we had big breakthroughs in understanding, it is because we started to measure something that we didn't know whether it was useful or not. This is an example from plate motions. There are a whole bunch of reversals of the Earth's magnetic field. But for plate tectonic reconstructions, we never use them. We choose one every 5 or 10 million years because, plates don't change motion very rapidly. They're huge. Until Chuck de Metz and Merkuriev used legacy Russian data. The Russians have enormously detailed data from the oceans because they used it in the Cold War to figure out where atomic submarines were. And they used those data and made very high resolution reconstructions of the India-Asia